All right, continuing with arc length and curvature. Okay, we have another formula for curvature. So the next one here is if you have R of t again, your curvature is a function of t, can also be r prime of t crossed with r double prime of t, and take the magnitude of that over r prime of t magnitude cubed. Okay, and again, this is going to be the same as the magnitude of the unit normal vector derivative over r prime of t. Okay, and that's the same as the magnitude of r prime of t over the magnitude of r prime of t over what a mess, huh? Okay, because this is that numerator here. Let me use a different color here. This is the same as this, right? T prime of t is r prime of t over r of t. So the magnitudes of each of those, right? So we definitely are not going to get into any kind of a proof of this, but there you go. Okay. So 3, you can choose, right? I mean, all of them just use r of t to start, and you find the derivatives and do whatever you need to with them. So you can pick and choose which one you want to use. We'll do, let's see, an example here. We can do, oh, and there's a proof for this if you want. The proof is on page 595. Okay, but here's an example. We're going to find the curvature of ti. Oops, I'm going to do r of t equals r of t equals ti plus t squared j plus e to the t k. Okay, so again, you can use whatever formula you want. Okay, they all require you to find r prime of t. Okay, so r prime of t would equal 1, 2t e to the t. Okay, and it's almost like go ahead and do it as an exercise to find it in the different ways. It's good practice. Our double prime of t would be 0, 2 e to the t. Okay. Then we can do the cross product of those. So that's going to be the determinant. Okay, so we'll have 2t e to the t minus 2e to the t. And then negative e to the t minus 0. And then positive 2. Okay. If you want, we can simplify that out. 2e to the t times t minus 1. Negative e to the t 2. Okay. The magnitude of that will be the square root of, let's see, 4e to the 2t, t minus 1 squared, plus e to the 2t, plus 4. And then the magnitude of r prime of t will be the square root of 1 plus 4t squared plus e to the 2t. Okay, so we end up with the curvature will be the square root of 4e to the 2t, t minus 1 squared, plus e to the 2t plus 4 over the second square root here, but then cubed. So you might just write it as 1 plus 4t squared plus e to the 2t to the 3/2. Okay, it's messy, but that's the answer. Again, if you wanted to, you could do it the other way. Let's see here. How tough is it going to be if we did t prime of t then would be r prime over its magnitude. So it would be 1 2t e to the t over square root of 1 plus 4t squared plus e to the 2t. Yeah, magnitude of that we'd have to find. Okay. Again, we need the magnitude of that. So we'd have to square everything and square root it. So it'd be the square root of 1 plus 4t squared plus e to the 2t, right? And then over, oh, I'm going to get messy here, aren't I? Oh, I see what I did wrong. I didn't do, no, I want r prime of t over that. Oh, I'd have to square everything. Yeah, it's going to get messy. So, you know, you don't want to do it, right? Okay. But this does lead us, this formula leads us to another curvature formula. Because I know you probably were like, give me another one. This has not been enough formulas for curvature yet, right? So, and this next one will be useful if you have a function that's in rectangular form. So if you have like a y equals f of x, okay, we can use it as vectors, where r of x would equal xi plus yj. Okay, so you get your x and your y. Okay, and give you your x component and your y component. And remember, the reason that we're using x there is because you would plug in, right? You plug in a value of x. So just use x as your parameter, right? Then your x component is x, and your y component is f of x. Okay, it's that easy. And so then r prime, of x would be 1i plus f prime of x j. And you can see that's how we got that rectangular form for arc length. Okay, there's 1 plus f prime of x. Okay, and then our double prime of x would be 0i plus f double prime of x j. Okay, or I guess I want to keep these in y. This would be the same as I plus y prime of j, and this would be y double prime of j. Just different notation. Okay, so if we go back to that curvature formula, the magnitude of r prime of x crossed with r double prime of x, it doesn't matter if it's t, x, theta, whatever, okay, over the magnitude of r prime of x cubed. Okay, so we can get the cross product of these guys. So r prime of x crossed with r double prime of x will be the determinant of we are going to do, well, it's only 2 by 2, so we only need 1 y prime and 0 y double prime. Okay, so that's y double prime. Okay, so this would just be the magnitude of y double prime over the magnitude of r prime. Here's your r prime, 1 plus y prime. Okay, so 1 squared plus y prime squared, square rooted, and then cubed. Okay, so this will be the same as f double prime of x magnitude over 1 plus f prime of x squared to the 3 halves. Okay, so there's your next formula. So this is nice when we have a function, not a vector. Okay, so we can do an example. Find the curvature of y equals x cubed. So think about this one for a second. If this is the track and you got a little roller coaster on the track, when is the person on the outside getting shoved around a lot? Okay, and you can kind of predict it's not happening here or here, and even not so much here. You kind of like, that's where you're going to have that straightening out a little bit. It's going to be here and here is where the curvature would be the greatest. Okay, but we're going to go ahead and use that formula. So let's get a different color here. Y prime would be 3x squared. Y double prime would be 6x. Okay, and that is the magnitude of y double prime. That's it. Okay, so the magnitude of y double prime would also be 6x. That's how it's going to work. So then your curvature would be this piece. Okay, so 6x over 1 plus 3x squared squared, so 9x to the 4th, okay, to the 3 halves. All right, and we can see a couple things here without having to look too much at that equation or not having to graph it. We can see a couple things. If x equals 0, the curvature is 0. Okay, so that spot right there, and that should make sense. You're kind of switching curvature, okay, from what you're doing in the third quadrant to what you're doing in the first quadrant. Another thing to notice is that the limit as x goes to positive or negative infinity of the curvature is also 0, because that denominator just blows up. Okay, so that's where we're getting those ends there with no curvature. If you were to actually graph it, okay, if you were to graph this, it has maximum values at positive and negative 0.386. Okay, and that's the spots right here and here where we're going to have maximum curvature. Okay, so definitely kind of mess around with graphing those and getting a good look at them. All right. Last thing we're going to talk about is some terminology. Gets kind of confusing in 3 dimensions, but we'll do our best here. We have normal and binormal vectors. Okay. One thing to keep in mind when we're talking about these is just the 3D nature of everything. Okay, the fact that if I draw a curve, it looks 2D, but think about the fact that it can also be like coming out of the screen towards you. So if I have like a curve like this, kind of think about the fact that one piece of that could be higher out of the screen than another piece. Okay, and I'll try to draw that with 3 dimensions. But we've got our, so let's say this is r of t. Okay, so we have our tangent vector, our unit tangent vector. t, which is r prime of t over the magnitude of r prime of t. Okay, so if we pick a point, let me use yellow here for a point. Okay, that unit tangent vector at point, what do I want to call it? I think I'm going to call it P. Okay, so P is a point on our curve, and our curve is R. Our unit tangent vector would look like that. Okay, then what we have is what's called a unit normal vector. So N of t, which is t prime of t over the magnitude of t prime of t. Okay, and that normal vector, it's going to point towards the concave side of this curve, and it's going to be normal to tangent. Okay. All right. Then we have, and sometimes I guess this is called a principal unit normal vector. Okay. Then we have another vector that is called the binormal vector. Okay, it is orthogonal to both t and n, and we know from our earlier sections then that b would be the cross product of them. Okay, so b might be like this. Okay, and you have to think about the fact that these would all be kind of 90 degrees from each other. Okay, they're almost making like your little, it's hard to draw the red one perpendicular to the purple one, but basically they're making a little coordinate plane wherever your point is. Regardless of x, y, and z, it's giving you that little x, y, z axis kind of, okay, a little point of reference there. So a couple things that we're going to write out here, and I'll kind of keep scrolling back up to that if I need to, okay? The plane determined by n and b. Okay, so the purple vector and that red vector. Okay, so if you can think about the plane determined by that, and not just in like a first quadrant, but think about that whole plane, okay, that b and n would lie in. It's perpendicular to t. Okay, you can think about like if I drew that yellow plane, t is coming like straight out of it. Okay, so plane determined by n and b is the normal plane of C, which is our curve. Okay, at P. It contains all lines orthogonal to T. Okay. Next one, the plane determined by T and N. Okay, so T and N. So the blue one and the purple one here. Okay, so think about that plane that would kind of like lie flat on top of the curve. Okay, is the osculating plane of C at P. Latin, osculum is kiss. Okay, so it comes close to containing the part of the curve near P. Okay, so if we're kind of like thinking about like cropping the big picture in as you get closer and closer and closer to P, that osculating plane comes closest to just mimicking what is happening at P. Okay, next, one more thing, and then we're done with all this. The circle that lies in the osculating plane of C at P and has the same tangent as C at P. Okay, so if I think about following the curve of C and the curve of the circle, they line up. Okay, and lies on the concave side of C and has a radius of 1 over K, where K is the curvature, is called the osculating circle of C at P. And that circle, also kind of like the osculating plane, the osculating circle, it describes how C behaves near P. Okay, so again, if we have a curve and we have a point on the curve P, hold on, curve, and we have a point P on the curve, if we meet these criteria here, so it has the same tangent. Okay, so the tangent here has to match the tangent of the circle. Okay, it's on the concave side, and the radius here would be 1 over K. So it's the that's your osculating circle. So the osculating circle will get smaller depending on the curvature. Okay, so there you go, all that terminology for that. And that is it for chapter 10.